Welcome to the thermodynamics lesson on the ideal gas law. Let's start off with what does it mean to be an ideal gas? An ideal gas is one in which all collisions between atoms or molecules are perfectly elastic and in which there are no intermolecular attractive forces. Like gases like nitrogen, oxygen, even carbon dioxide, at high temperatures and low pressures tend to act like an ideal gas, whereas heavier ones, like the ones in refrigerants and even water vapor, tend to not act like an ideal gas in certain conditions. So it is useful to talk about these hypothetical gases and their interactions of their pressure and their volume, temperature, etc. So these requirements for an ideal gas come from the kinetic theory of gases, which I'm sure we'll discuss more in class. All right, the ideal gas law has an associated equation that goes with it. And that equation is PV equals N capital R capital T. Highlighting the variables here, we have pressure, capital P, and the units of pressure are always in physics pascals or in newtons per meter squared, which is the same thing. Those are the standard SI units. However, in our unit here in thermodynamics, you may also see units of atmospheres. And on your reference table, there's a conversion between pascals and atmospheres, in that 1 atmosphere is 1 times 10 to the 5th pascals. Pretty simple conversion. V, of course, stands for volume. And our units of volume in physics are meters cubed. However, you will commonly see units of liters also used, and we'll talk about, when we get that far, how to convert easily from liters to meters cubed. N, you chem people will recognize as number of moles. That's the number of moles of the gas. Capital R is the universal gas constant. We really need to pay attention to the units of this, and in physics the value of the universal gas constant is 8.31 joules per mole Kelvin. From this drives our units of temperature, which is our symbol capital T. And because of the units in our gas constant, whenever we use the ideal gas law, our units of temperature have to be in Kelvin. Okay? And if you're given that in degrees C, just a quick reminder, you take your temperature in degrees C and you add 273 to get your temperature in Kelvin. All right, the ideal gas law becomes particularly useful when we want to compare a gas in some initial state to that same gas in some final state. So writing the equation in the initial state, we would have PO/VO equals nRTO, and in some final state it would be PV equals nRT. If we wanted to compare them, we could say, okay, put nRT in the denominator of both sides, so you'd have PO/VO over nRTO, and if you're comparing that to some final state, you can now say equals PV equals nRT in some final state. Well, what's really important here in order to do this is that you have the same number of moles that you started out with in the beginning and the end. And if that's true, the N cancels. R is the gas constant, so it cancels. And what you, of course, get here is a relationship of PO/VO over TO equals PV over T for the ideal gas in some initial state compared to the ideal gas in some final state, which means you can make changes to it and see what the resulting changes in these variables are: pressure, volume, and temperature. Okay? To do that, we would put the gas through a number of possible thermodynamic processes that we're going to talk about now. And those processes are either isobaric, isovolumetric, also called isochoric, isothermal, or adiabatic. We're going to talk about what each of them is and the resulting ideal gas law equation that corresponds to that. Isobaric is a process, thermodynamic process, that the gas goes under constant pressure. And if that's true, in our analysis there of PO V over TO equals PV over T, the P's would be the same on both sides. Isobaric should be easy for you to remember. Iso means same, and baric you remember from barometric pressure. So not a leap there for you to remember that isobaric is a thermodynamic process under which an ideal gas undergoes that process at constant pressure. If that's true, then we would have VO over TO equals V over T, since the pressure is the same on both sides and would cancel. Isovolumetric, also called isochoric process, is one in which an ideal gas undergoes the process at constant volume. In this case, of course, the V's would cancel, and you'd get PO over TO equals P over T. Isothermal process, just as it is implied, is a process that the ideal gas undergoes under constant temperature. That's true. The T on both sides cancels, and so you get PO/VO equals P times V. No temperature in the equation since it cancels. Then our fourth possible thermodynamic process is called adiabatic. Adiabatic is when the gas neither gains or loses heat. And you may say, may ask, what's the difference between adiabatic and isothermal? One of the biggest hurdles to overcome in thermodynamics is to understand that temperature is simply a measure of the average kinetic energy of the molecules. Yes, there is usually a corresponding relationship between heat and temperature. Generally, when we gain heat, that causes the molecules to increase their kinetic energy and the temperature rises. And when a gas loses heat, it generally causes less kinetic energy of the molecules and therefore indicated by a lower temperature. But not necessarily. We will see cases in which heat is gained or lost by an ideal gas, yet the gas remains the same temperature. Okay. Lastly, I'd like to finish up here by showing you a neat little simulation, and the URL I pasted in here. I don't know that with your iPad you'll be able to do that because it generally doesn't support Flash animations, but this is a really neat, and I'm going to slide over to my computer here and do a quick overview of this simulation, how it can be used by you in understanding the relationships of pressure, volume, and temperature with an ideal gas. More to come here in a moment. Here we are now at the simulation using the URL provided earlier. You have to probably do this on a PC in order to see it well. Really neat though, what you have here is a container that you can open or close. You can also expand the size of the container and change the volume. Over here you can select various parameters of volume, pressure, or temperature to remain constant or not. You can change between being a heavy gas or a light gas. We're going to do a light gas here since we're doing ideal gas law. So you pump the handle here, okay, and you put some gas in there, and it gives you some neat parameters once things stabilize. Temperature is 300 Kelvin. Pressure is in atmospheres, nearly an atmosphere, about 0.9. Okay, and it tells you how many molecules of gas you have, 156 in this particular case over here. Some things you can do to show and understand the relationship. If you add heat, okay, what you see, of course, happen is that the temperature rises. Okay, add more heat. You can see it start to expand the container a little bit on its own, so the gas is doing the work. We'll talk a lot about this later. Okay, if I hold it to that value, you can see what happens is the little guy over here is trying to hold that. Blew the lid right off the thing. Okay, a lot of neat stuff you can do. So anyway, by keeping various parameters constant, you can see now that the volume can't be changed, okay, or that the temperature is to remain constant, or the pressure is to remain constant. You can do these isobaric or isothermal or isovolumetric processes, add heat, understand the relationships of what happens to the other ones that don't change. Really neat simulation. I would encourage you to use it. Go back and use it when we have some of those problems later on that you're trying to solve and maybe trying to gain some understanding of with the ideal gas law. All right, that'll wrap it up. We're going to start solving some problems here using ideal gas law and some other concepts. So more to come in class tomorrow.